Hello, and welcome to this introductory video on understanding the photoelectric effect. In this video, what we're going to do is take the results that we established, or what happens when you conduct a photoelectric experiment, and try to make sense of them by just updating our understanding slightly further than what we took when we were discussing it from a classical sense. And admittedly, our classical interpretation already included a little bit of a cheat in order to discuss what you might expect happens with frequency. So we started off with this sort of setup, and we said classically we had certain expectations, and it basically all amounted to just saying what happens, how soon do you get that current, and how much current do you get. Those were sort of the only two things that we were playing around with. There was no minimum frequency to do anything. You just had to wait longer, things like that. And then, of course, in reality, what we found was that there is very much a minimum frequency. And basically, if you were at that frequency, you didn't have to wait at all. You got a current. And if you weren't at that frequency, if you were below that frequency, then you never got anything, no matter how long you waited. So we need to make sense out of this, but it requires two ideas from quantum mechanics. One of them we've actually secretly already used, and it's this thing here. This looks pretty continuous, but it's actually quantized the energy of a photon, and it said that light is indeed coming in these little packets of photons that have energy E equals hf. That's half the story, but of course, by itself, it doesn't explain things, because you would still expect, as we discussed in the earlier video, these sort of weird currents that just appear after a while. So that's half the story. The other half is understanding that even the energy of the electrons is also quantized. So quantized always just means that there are certain allowed values for the energy and certain other ones that you cannot have. So if we think about this typical picture of having some sort of electrons orbiting around atoms, they've got certain energies, which are basically the binding energies. And we can think about that for this metal plate too. There is some energy holding the electron as in the metal, and we call that the binding energy. Now this binding energy we'll just talk about as BE. So there's some binding energy that we need. In other cases, you might hear this binding energy talked about as the work function of the metal. Basically, it's the same idea. Remember that work and energy are equivalent. You have to do a certain amount of work to give something a certain amount of energy. So if we're saying that we need to give an electron an energy of BE, the binding energy, in order to escape the metal, well, that's the same as saying there's some amount of work W that we have to do on that electron in order for it to then be free of the metal. So binding energy, work function, whatever, that is the minimum energy that you have to give the electron to escape. Having just said that is not enough, because then you're still saying, oh, well, I'll dump in E equals hf each time. I can eventually overcome the binding energy. So you're still in this classical picture. So the trick is, though, that these electrons are only allowed into certain energy levels. What energies can the electron have in this metal? Well, it might have, I don't know, something here without any actual values, something here, and maybe up here is when it is free of the metal. That's how much energy you need to become free. Then this binding energy we're thinking of is the minimum energy to go from this bound state. So all of these down here are bound states. These energies are not enough to be free, but they are allowed in the metal. This last one is the closest to being free, and this difference between here is what we mean by the binding energy. So we have to give it that much energy in order to escape. Now, this diagram then finally removes this sort of thing. We've said the electrons are in discrete energy levels. We've said that the photons have energy E equals hf, and in particular that each photon is a real particle with that energy. So, okay, what does that mean? It means that this electron, waiting down here to be free, must get at least the binding energy in one interaction, because it cannot take a small fraction of the binding energy and sort of store it and go to here. That's not allowed. There's no level there. You can't go there either. You can't go there. You have to go all the way up And then actually you can go free, because once it's free, you can actually be at any energy you like, once you're no longer in this weird system that has quantized the energy. So the free particle can have any energy. So I can give it the binding energy, then I've gotten just free, or I can give it anything more than the binding energy, but I cannot give it anything less than the binding energy, because there's nowhere for it to go while it's storing that energy. It cannot store that energy. This quantization means the electron has to get at least that much. The other thing that you notice is you're not allowed either to sort of interact with multiple photons or fractions of photons either. You must always be grabbing E equals hf from a photon, and that photon then is completely used up. You've taken all of its energy, you've absorbed that photon. Which means that I cannot say something like, oh, but if I take 5 photons at once, then I might have enough. You cannot do that. It has to be a one-to-one interaction and get free. So now what that means is, if E equals hf is equal to the binding energy, well, then that is the minimum frequency in order to turn this thing on. And so that F0 nicely explains this threshold frequency we have here, making that F0. Okay. And then it also explains why it's either you had current or you didn't have current. Because if F is less than F0, then you're looking at a case where the binding energy is greater than the energy you're putting in. So you're talking about trying to get here somewhere in this diagram. The electron can't do it. It ignores those photons. On the other hand, it also actually explains what's going on with intensity. Intensity doesn't change the frequency of the light. It changes how many photons you've got. And we've talked about you have to go one interaction at a time. You can't grab 5 photons. So changing the number of photons doesn't help. If the frequency is too low, the electron is still always just trying to go over somewhere in between. You can't do that, so the electron ignores each and every one of the now suddenly more photons, even though I've doubled the intensity. So intensity doesn't help you get current. On the other hand, if the frequency is high enough, so it's F0 or more, well then I'm talking about taking electrons that are in this level and moving them into this continuum, into the free part of that energy level diagram. And that then means that those electrons are free of the metal. And each photon can individually free an electron. So if I increase the number of photons by increasing the intensity, then I have indeed freed more electrons and increased the current. So the key here was 2 things. One was that the energy of the electrons in the metal was quantized, so was only certain energies. And 2, photons exist, so there's light is particle, they have energy hf. And so since we made light into particles, discrete packets of energy of hf, and we made the energy levels in the metal only certain values, basically those 2 amount to saying, 1, that the energy of the electron is quantized, and so too is that light is also quantized. And that is the start of quantum mechanics, where you are taking things which in classical mechanics were all nice continuous values and turning them into discrete things. So we've made light discretized packets of energy. We've made the electrons have discretized energy levels. And as a result, we can explain and predict things about the photoelectric effect, and we get them right.